Hello, everyone. I noticed that I'm the second Yuval in this session, but I promise you it's a different talk. So I appreciate that the audience here is quite diverse. Probably there are hardware experts that want to understand how to scale to fault-tolerance quantum computing, but there are also curious end users that just want to understand what can we do with quantum computers today. So I'll try to give you in this talk both these angles. What is possible with today's computer, and give you some insight regarding the future and fault tolerance. You probably heard it millions of times already. The biggest challenge of quantum computers is noise. Hardware errors lead to algorithmic failure. And this is the problem that at Q-Control we are uniquely focusing on solving. We build infrastructure software that connects the low levels of the quantum computing stack, the hardware, the classical controllers, with the top layers of the quantum computing stack. For example, the application layer. And in this middle part of the stack, we host our technology that we build in-house. And the goal of this technology is that whenever you want to run an algorithm on a real quantum computer, we'll make sure that it is executed faithfully and the results that you get are meaningful. Last year, exactly last December, we were very happy to be able to announce our collaboration and partnership with IBM, where all the tools that I'll be telling you about in the next few minutes became natively available on the IBM Quantum Services. And all you need to do in order to use them is to add one line of code to your already existing code. And of course, beside the excitement of having a billboard in Times Square, we were also very proud to be the trailblazers, to be the very first independent software provider to integrate with a hardware provider. And this is not our last, so we're also very happy to announce that coming very soon, we're also going to integrate natively our tools into the Rigetti system. So if you are using a Rigetti devices, you can just use the Q-Control tools with, again, one line of code. And under the hood of our technology, we built a completely autonomous pipeline that suppresses errors everywhere they occur in runtime, not in post-processing. Historically, the task of suppressing errors was on the users. We expect them to design algorithms, map it to quantum circuits, understand the hardware, and then do all kinds of techniques and tricks to mitigate the noise on these devices. And that's quite hard, because errors creep into algorithms in all different levels. We optimize all the way from pulse level and gate level to circuit level and all the way to compilation. And that's quite hard for a typical user. So beside lowering the barrier, the most important thing is the value that users see by using our tools. And just to be clear, these numbers are not numbers that we at Q-Control cooked up in a dark basement. These are not numbers for use cases that we tailored specifically to make our tools shine. These are not research projects that our researchers worked for 6 months and cherry-picked the right results. These are the numbers that our users see by running their use cases without our involvement with our out-of-the-box tool. They see 10x improvement in the circuit depth before losing a signal. They see over 1000x improvement in the number of shots and cost that they need, mainly because our tools are deterministic. They don't need any overhead, and the signal-to-noise ratio is much better. And they see over 1000x improvement in the actual performance of algorithms. And one such use case came from Mitsubishi Chemical. They recently published a paper showing that they can accurately calculate the ground state and excited state energy of a non-trivial molecule with 33-qubit representation. And Shu Khanna from Mitsubishi Chemical was kind enough to share his experience. He said, "We achieved a significant leap forward in accurately calculating the physical properties of material, demonstrating a 5-fold increase in the achievable circuit widths over previous quantum phase estimation studies. These results were enabled by Q-Control's performance management, which made it possible to run deeper and wider circuits on IBM systems." Beside material science and chemistry, we also identified optimization as another use case that may give us advantage in the near term. We worked with different partners to demonstrate that across different kinds of problems. For example, with Network Rail of the UK, we demonstrated a timetable scheduling, convoy route optimization with the Australian Army, real-time transport routing with Transport for New South Wales, and different kinds of logistics problems, including the one presented by Airbus and BMW recently. And in order to tackle these kinds of optimization problems, the approach that we take is to use hybrid algorithms. And the main idea behind hybrid algorithms is to use both classical and quantum resources. And there are two reasons for that. First, we don't want the quantum computer to do tasks that classical computers will always do better. And second, we want to make sure that the amount of resources that we currently need in the algorithms is compatible with the quantum resources that are available to us today. The main challenge with quantum algorithms is that it's not an algorithm, it's a framework. And there is a whole zoo of algorithms that probably you are familiar with some of them. And also in this case, historically, it was on the user to do all that. The users were expected to understand the classical problem, map it to a quantum problem, then choose an algorithm, create the circuits, make sure that every time they run the circuit is executed faithfully, tune the classical optimization loop, and finally understand how to even read the information from the quantum computer to deduce something about their problem of interest. That's quite hard and not a very realistic expectation from a typical user. So we replace all that and take that load on us with, again, our solver, which is one line of code that all you need to do as a user is to define your problem, objective function and set of constraints, exactly like you do when you submit a problem to a classical solver like Cplex or Gorobi. And our solver is natively available right now on IBM system and will soon be available on Rigetti as well. We benchmark this solver across many different kinds of problems. Many of them are summarized in this paper just from a few months ago. And I highlighted a somewhat controversial statement that we had there, that we claimed that for the first time we identified a set of optimization problems where a gate-based quantum computer outperformed an annealer. We tested a large range of problems. So the first set of problems that we started with are the hydrogen atom of optimization in some sense, Kuba problem, quadratic, unconstrained optimization problems. They appear in a wide range of commercial use cases, and they're very amenable to quantum computing. That's why most of the publications that you see around quantum optimization typically deal with Kuba problems. And the most canonical Kuba problem is MaxCat, that is practically serving as a benchmark these days for these algorithms. This is what you see when you run a large MaxCat on a real quantum computer using vanilla QAOA or some of the more common optimizations. So here you can see the samples. This is the red blob, the solution that you sample from the optimal circuit. And the point is that this is not very distinguishable from random sampling, and even more importantly, look how far it is from the true solution. Quite far. When we add the software, our software, on top of that, the same quantum device with the same quantum problem, we are getting a state that is much, much better, and in particular, we recover the true solution of the problem. This is, of course, one problem. We benchmark that on a huge series of problems, many different number of qubits, graphs, densities, weights. 100% of the time, we were able to recover the true solution, even in cases where competitor hardware and competitor software were not able to find it. Of course, we want to go beyond Kuba, because that's not enough. So one way to do that is to go to higher order optimization. This is a problem that we borrowed from the open literature. This is a paper from a paper published by the Los Alamos group, where the challenge here is to find the ground state configuration of an Ising spin glass with linear, quadratic, and cubic terms. So the starting point is the gray distribution. This is a local solver, something like simulated annealing. And as you can see, the results are not great. Then the purple distribution is what you get when you run our algorithm on a quantum computer. So you see a much better distribution. And in particular, we recover the true ground state. Now, I want to make clear there is no advantage here because the true ground state was calculated with a classical solver that was calculated with Cplex. So commercial solvers like Cplex and Gorobi can still easily find the solutions for these problems. But for example, open source solvers like simulated annealing that are very common in academic settings already fail to find the solutions for these kind of problems. The interesting thing is that for this specific instance of spin glass, we also had the best result achieved by a quantum annealer. This is the green line. And while it's a very good result, it is not the optimal state. Of course, we also need to be able to go beyond non-constraint optimization because real-life problems typically have constraints. And just recently, we were able to demonstrate a quite large optimization of Q-sub problem. These are quadratic semi-assignment problems, which are very common in logistics optimization, where we show that even though in this case the classical benchmark was able to find a solution, we boosted by over 11x the probability of finding the solution. And one last point that I want to make is the importance of having an ecosystem where an end user bring their problems to us, and then we can understand how to solve these problems. And this is a very nice example where AFS had a need to identify security threats in their data. This is a classical machine learning problem. So together with AFS, we worked to frame this machine learning problem as a pipeline that includes an optimization problem, and then we solve this optimization problem using our software, FireOpal, on Amazon Braket connected to an IonQ device. So the full hybrid loop was done via Amazon Braket, and everything was done on the IonQ 25QB device. No simulators, no classical compute. And also in this case, the classical benchmark was able to find the real solution, the true solution, but we were able to boost it by a factor of 3. All right, so this is what is possible today, but what's next? How do we scale? And we know that as we scale up, error suppression alone is not enough, because even if we prevent all the errors that we can, some errors are just inevitable. And for that, we'll need error correction. So I'm going to slightly contradict the other Yuval from the other talk, and raise a point that is maybe a bit delicate in this room. And the point is that while we saw truly tremendous demonstrations of quantum error correction beyond break-even, the reality is that quantum error correction will not be the method of choice for most users for still many years to come. And that's because the amount of resources that quantum error correction needs are huge. The amazing Google experiment used the whole device to generate one single qubit, not even operational qubit, just memory. Just yesterday, we heard from IBM, a single shot of the gross code is more than an hour compared to 4,000 shots in a second that you can do today, over 10 million gap in time. For most users, that means that it will still take quite a lot of time before you'll start using quantum correction. So the question is, what is the answer for that? And you can probably imagine that the answer for that is not to add extra mitigation on top of that. You don't want to add exponential overhead to something that is already quite heavy to run. What you want to do, you want to try and understand how do you reduce the load that you require from quantum error correction. And one answer to that is to use aggressive error suppression together with error correction. In analogy, we think about using error correction alone as trying to cool a room in a hot day while leaving the windows and door open. You are going to work very hard, and the results are not going to be great. Using aggressive error suppression in runtime together with error correction is equivalent of closing the doors and windows, and you'll be able to cool the room with much less resources. And there are many demonstrations along that. For example, this is a demonstration from Nord Quantique. They had a specific type of quantum error correction scheme, and when they ran it, they noticed that the gain that you get from the quantum error correction and the penalty from applying the error correction exactly cancel each other, and the performance is pretty much the same as the physical level. But when they added our tools on top of that, the optimization and error suppression, with no further overhead, they saw results that are beyond break-even. And if you want to hear about more demonstrations of this kind, please join me tomorrow in the error correction session. But in the last few minutes that I have in my talk, I want to talk about a slightly different thing, a different angle. Instead of asking, how can we use error suppression to help error correction, can we ask the opposite question? Can IDs and primitives of error correction can help us today improve the performance of quantum computers with the resources that we have today, not with the resources that we'll have 20 years from now? And the answer for that is yes. Just a few weeks ago, we published a paper that showed that. We show that by using error detection, which is, of course, one of the basic primitives of quantum error correction codes, at the physical level, can dramatically boost the performance of algorithms. Now, of course, you lose a lot when you don't encode. You lose generality, you lose sensitivity to all errors, you lose the ability to correct in runtime, but you also gain a lot. Instead of having 10, 100, 1,000 of X overhead, you only have something between 0 to 20% overheads. And these are overheads that we can handle today and not 20 years from now. So in this paper, we showed several examples. I'll just take you through two of them. The first one is just generating a large entangled state, GHZ state. And the first thing that we are looking at is the Hellinger fidelity, which is just a measure of the diagonal of the density matrix. It is one if and only if the two populations that you care about, in this case the all 0 and the all 1, are exactly 50-50% matched. And the interesting thing is that this measure is sensitive to the errors that we detect. And as you can see, even when we go to 60 qubits, we are pretty much perfect, which means that our detection is extremely efficient. Of course, our detection is blind to some kinds of error, like phase errors, and for that, we need to measure a different kinds of fidelity that is sensitive to the whole state and to the actual entanglement that we are generating. So we also measure the MQC fidelity, which is agreed that any value beyond 50% is considered as a successful generation of a genuine multipartite entanglement state. And we show that we can generate states with genuine multipartite entanglement all the way to 75 qubits, the largest to date, larger than any demonstration with logical qubits. And in this case, we are seeing about 60% of MQC fidelity, about 3x boost compared to the best method on a physical level without error detection alone at all. And in order to achieve that, all we needed to have is only 12% overhead in qubits. These are the flag qubits that measured the detection, and only 78% discard rate, which I know it sounds a lot, but many of the recent demonstrations of quantum error correction were deep into the 99% discard rate. So this is relatively mild. And then another demonstration that we had is around teleportation. We designed a specific teleportation protocol that allowed for error detection. And then we compared it against existing protocols. In this case, it's a teleportation of a CNOT gate. We want to teleport a CNOT from one red qubit in one corner to the other red qubit in the other corner, where there are some number of qubits in between. And this is the numbers that you see on the x-axis. And we compared it to the best existing protocols that by themselves outperform any swap strategy protocol. And as you can see, we can outperform them by a quite large margin. In particular, we see 90% CNOT fidelity when there are 30 qubits between the two qubits of interest, and close to 85% fidelity when there are 40 qubits between the two qubits that we are teleporting between. So the last thing that I want to mention is that there are different phases in the development of quantum error correction, and we are all very thrilled and excited kind of to move from the NISQ era to an era we can actually demonstrate beyond break-even experiments. But we need to remember that just beyond break-even is not enough. It's actually far from being enough to be useful quantum error correction, where people will actually use quantum error correction in order to run their algorithms and see better results than any alternative methods with relevant resources that exist today. And resources is number of qubits, is time, is number of operations that you need to do. And the question is, how do we bring the quantum error correction advantage era, where people will actually use it, closer? And at Q-Control, we are devoted to push that forward, both help people achieve demonstrations of beyond break-even now, but also bringing the QEC advantage era a bit closer. So if you are interested and you want to hear more about these things, you can find us at our booth or just contact us. And with that, thank you for your attention.